Our next speaker today is Dolan of Deep6 AI. He is Deep6 AI's chief scientist and co-founder. Brian has led enterprise analytics projects from design to implementation for clients like EMC, SuperValue, Northern Trust, Zions National Bank, Havas Media, T-Mobile, the U.S. Intelligence Community, and Research in Motion. He will be presenting a talk titled A Practical Use of Artificial Intelligence in the Fight Against Cancer. Please join me in welcoming Brian.
Again, I'm Brian Dolan from Deep6 AI. You can get me at Brian@Deep6 AI if you feel like contacting me. I'm generally pretty responsive. I don't have a lot of business cards, so I would really like to talk to everybody who's interested, but I probably won't have time to do it. So thank you. So what we're going to talk about today, we're going to talk a little bit about Deep6, what we do. We're going to talk a little bit about why are we using graphs. I'm going to introduce why we're using graphs in a moment. We're going to talk a little bit about the applications of graphs, guidance on using natural language processing, my stage-like wisdom, which I already shared with you in the form of blank slides, and then hopefully we'll get some Q&A going, because I love answering questions. I miss teaching. Next slide, please. What we're not going to talk about, we're not going to use the C word very much. I know it's in my title, but I don't like saying it. This is my mom, right here in the green, my son, my nephew, that's my sister. My mom was taken by cancer, my sister is in the hospital today having a tumor removed. So I don't like that word. It makes me angry when I think about it. But it also gives a sort of gravity to what we're doing and why we're doing it. I was in advertising for a while. I was in a lot of different things. I was in a lot of things that didn't feel as frustrating when you fail. But here, when we're dealing with cancer trials and people dealing with cancer, it really hurts when you fail. I like to say the word, so hopefully this is the last time I'm going to say it, might slip out. Next slide, please. Thank you. So who is Deep6? Deep6 AI, we're an artificial intelligence and natural language processing company. In a nutshell, we use natural language processing to create concepts, and then we use artificial intelligence to do analysis upon those concepts. So we show you some graphs with those. Normally we think we've extracted from the natural language processing, and the idea will be the artificial intelligence aspect. I'm going to give you a couple nuggets on things that I just learned. It's been pretty exciting. And give you some ideas on how hopefully we can use folks to do it. So two questions that come up is, if you're matching clinical trials, why is this important and why is it hard? So let me talk about why it's important. First of all, if you're a researcher, say even here at medical school, and you have a brilliant idea on how you're going to attack prostate cancer and how you're going to cure it once and for all, the only way you can get your idea through approval and in the market and save lives is by going through clinical trials. You have to invite people in and say, let's try this, deliver it, yes, no. Clinical trials, the last step for all pharmaceutical companies, all research universities, between us and potentially life-saving cures. It's an important topic that we're dealing with. So the problem is that in 2015, we needed about 6 million people to get into trials, and we were short almost 4 million. That's 4 million opportunities to test out new drugs for life-saving cures. 4 million opportunities. There's an economic price to pay on that, which when we're doing our investor pitch, I can tell you is a big number. Big number when you list this, but it just sucks to know that we lost 4 million chances. And this year, we're keeping 2 million, we're at 6.7 million. We need that in this year, and we're not going to make it. So that's why what we're doing is really important. We're not putting melons on cats' heads here. We're trying to give patients the best possible care and save some money. So why is this hard? Well, patient data is really, really choppy. Some of the ugliest data I've dealt with, some of the most complicated data I've dealt with. One of the things that I was asked during a pitch, well, search is easy, right? And I was on my phone with the guy. Search is it's easy. Hey, I can download Elasticsearch or the scene. I can do that. I want to tokenize and look at a bunch of words, that's fine. But I don't care about words. I care about ideas. I care about process. I care about the fact that heart attack is the same thing as myocardial infarction to many people. Not to everybody, but to many people. There's no token of that whatsoever. When I'm looking at things, we have interrelated concepts. If I'm looking at how do we know we have prostate cancer, I don't want to treat anybody else. Look at somebody who said that. How do we know we have prostate cancer? Because it's been histologically confirmed. So the testing method and the treatments that you've been given are importantly linked to the concept that we're attacking. And that's not a search thing. That is a meta concept level. What we have to do is basically take things that are just tokens in, for instance, the doctor's notes, and identify how those tokens have a semantic context and relate to one another. When you look at this slide, you can see that it's a very natural representation to use graphs for that. And honestly, our research on graphs and using the three pillars of graph, like what you said, has really brought us a lot of attention. Graphs are a pretty important new method of attack. It's very understudied. Most of the stuff that you guys are doing now, or that everybody's doing now, or deep learning and statistical community is mostly object-oriented, matrix-oriented stuff. We're dealing with the covariant structure of graphs. It's a very new field. There's not a lot of machinery there in general on the machine learning side of things. Please next slide. So we feel like there are three pillars to being what's called a graph company. And part of our success being a graph company is that we've separated what it means to this determined. Again, when we're talking to investors about blah, just like a graph company. So you need three things. You need this pillar here. You need a database of some sort that can do traversals very quickly. This to this to this. When we were at CIA, we said, who knows? Alice was wrong and was checking. So those kind of traversals and graph database are really, really simple. You need graph analytics, a very old science established in 1786 with 1736. The first problem stated by Euler, remember that correctly, was how do you traverse 7 bridges without going over the same bridge twice and hit all of them. So one of the first, one of the earliest stated graph problems in a graph theoretic context. And that's when you need your graph processing system. There's lots of those out there. Our choice for right now, because it has a C++ binding, is iGraph. It's very good. I know a lot of people like Spark's GraphX failed for me on several pages. I don't use it anymore. Next slide. So, why graphs? This is going to go fast. So Jason's ready. All right. Why graphs? Well, as I talked about, what we're really interested in is the correlation structure between ideas. We're not really interested in atomic ideas. We're not labeling things up, things down. I'm saying these two things have a symbiotic relationship. So we're looking at this red dot as a patient, and these blue dots as potential features of that patient. They could be symptoms, or they could just be age and weight. This is not a mole. This is not a mole. This still not a mole. Even though we have all this structure here, this correlation structure, we still don't have any moles, right? But now, we have a stage 4 mole attack. The structure underneath, the stuff you haven't collected, the stuff you don't know about, or an extra body of knowledge that already has a correlation, a correlative analysis in it, that already has something in it, that interesting stuff, the thing on the side of the desk has a lot of information about how these things relate to each other. You see that within the graph structure, and it becomes immediately apparent that this subcommunity is an important part of your analysis. These simple correlations are extremely important. You don't know, and I'm going to show you an example, you don't know when you're going to walk into a room full of information. And the field of algebraic graph theory, which I'm going to introduce in just a second, allows you to attack those correlations you need. So, when you start talking about graph analytics, really there's a lot of language that we have to learn, and we have to move away from the traditional statistical analysis and machine learning and AI techniques. For instance, connectedness can go away from any node to another node. There's this concept associated with that concept. There's the degree of transitivity between this. That's a fairly interesting concept between this. And every time I walk down the street, I always go by my favorite coffee shop. So between this is an important part of understanding what concepts are pertinent within a body of patients, body of nodes. The community detection, something that we became familiar with when we were looking at data from CIA, or actually we were looking directly at data that we were looking on methods from. They were interested in things like first talking to who. And I'm not even interested in that, so they're interested in it. So you have a slide, who's talking to each other. I think we can. We even developed these methods, so we learned a lot about them. One of the things that's really interesting in using community detection is you can say, if I give you a piece of information, if I give a piece of information to that guy in this room, how fast is it going to travel over there? Or if I find a piece of information from you, where did it probably come from? So community detection is an extremely important part of graph analytics, and it's extremely important to our particular study. Because you might be a symptom, and you might be a manifestation, and I want to know how these things are correlated, how I can traverse back and forth between them. There's a lot of good stuff out there. This book is a great book. And unfortunately, I screwed up the title and the over, so sorry about that. I'm not bloating, by the way, my daughter put that there, so. I might tell you how to do it if you want to see it. Next slide, please. Oh yeah, I remember this one. So the first thing we do when we're translating from graphs and we want to get into this wealthy body of knowledge is we take a general graph, we'll call it, I don't know, G. It's a directed graph. Okay, you can see the arrows. It's a directed graph, and it says, hey, between A and B and A and E, I have a 1. A to B, everybody can see a 1, right? A to B, A to E, there's a 1 there. Extremely important difference between this and traditional methods. And we're going to say this a couple more times. This is an edge. This is not an object. Right? I'm dealing with the edges, the semantic structure of this data, not an object. I'm not labeling which one's up and one's down. I'm not labeling a person who has attributes. I'm saying, how is this person in a relationship to the next person? So I can find communities. When you take this X, and you start doing it as polynomial powers, which I like to do because it's fun, and it lights up all the little lights on the machines. I just got crazy computers just gave me access to one of their systems for a year, because they like what they're doing, and my goal is to use every electron they own. Actually, they do it. I got a little bit more on that later. So when you take X in, if I square this matrix, I'm going to get how many second order, two-length paths exist in this graph. So there'll be a 2 between A and B, because I've got A, E, B. And there'll be a 2 between F and B, but there'll be a 0 between F and G, for instance. Pretty handy. I now know how many paths there are of a certain order between any two concepts. And not only that, because, next slide please, or next one please, because I have a matrix, I can transform one graph by another. And just like that, I turn an arbitrary collection of nodes and edges into a linear algebra problem, which is an extremely useful thing to have in computer science, in case you haven't heard. But it's important that when you're doing your spectral decoms, you're doing your PCAs, your regressions, everything, you're not operating on the objects themselves. You're operating on the correlation structure of these objects. So one of the ways we get started on these is an extremely powerful method you can use, because now I can walk back and forth between graphland and the linear algebra land, which I've just decided is here. Maybe I'll remember. When you're looking at patients and symptoms, you can create a thing called a digraph. You can create a thing called a digraph that has patients on this side and symptoms on that side. And when I take the square, the transpose times itself, I can get the number of patients that have symptoms in common. If I take X times its transpose, X transpose X, or X times X transpose, gives me two completely different sets of information. All for free, all in matrix, all addressing the semantic structure of that data immediately. Next slide, please. I'm going to hurry because I really want to get to this one. This is one of those things that surprised the heck out of me. This is it's new to me. It's appears to be new to the literature. I'm hoping it's not. I can somebody out here goes, oh, Brian, you're an idiot. It's been around for 50 years because I don't know about it. But at this point, this is a pretty new thing to me. This is the first supervised learning routine I've ever done in my number of years of doing this that worked immediately out of the box. Like, bang, just worked. So here's the idea. I'm interested in this homographic and homonymic individuation of mole and mole. Is it a word? Is it a thing on your skin? Right? So the gene structure, the data itself, has lexical relationships, which means they're spelled the same, and semantic relationships means they're in a similar domain. But I don't know how to disambiguate that when I'm using my NLP, right? And there's lots of ways to do that, typically. But the best thing we found is to simply label the edges. So we label the edges, we don't label the objects. So now I'm doing the edge of the edge, right? And I find out that I say, hey, neoplasms of the skin and malignant neoplasms create a correlation structure between that and mole on the skin. And I downweight it between that and rodent. And that information suddenly percolates throughout the graph immediately. If you use, I'm leaving out two little parts. I'm not going to tell you them because I'm an IBM here. I've been IBM 3 times, so it's going to be my 4th. But this percolates throughout the graph structure immediately. It allows you to create this mesh of correlations. So anytime you come across a concept, you know the underlying manifold correlations that it exists upon. I would like to know if there's more theoretical support here. I have some. I'd like more. But this comes from the field of algebraic graph theory. It's a fairly fascinating field. It borrows a lot from the mathematics of quantum entanglement, which is kind of fun, I'll be honest. I'm just learning about it now. Next slide. Thank you. So, getting back to advice, practical advice, one of the things that I was able to do is because I built this method from first principles, I had to decide the domain. What do I want to know? What do I want to look at? So I was analyzing X transpose X to look at things in symptoms. I think we can skip the rest of the slide because it's kind of boring. Go except for this last one. This is semantic analysis. We talked about the semantic web. This is semantic analysis at a very basic level. Please, next slide. So the next topic that we work a lot on, I won't get 2 slides on this, natural language processing, where we have to disambiguate tokens. When you're reading a piece of text, you just know the letters RA. Does that mean rheumatoid arthritis? Does it mean room air? Does it mean refractory anemia? If you don't know what refractory anemia is, my computer does, I don't. So in NLP, we're often faced with this problem. Next slide, please. So, because I've been doing NLP for a very long time, I've found these are 3 of the things that break on me all the time. Not that they're bad, but you have to be careful that you're using them in the correct domain. The first one is negations in any non-trivial environment are non-trivial. So if I say, bring me a patient who has tested negative for sepsis, but positive for metastatic nodules, that's a very complicated piece of information to extract from the phrase, patient D tested negative for the following. Does this guy qualify? It's very hard to get. It's an ongoing part of research. And when you're dealing with like movie reviews or Twitter, it's not a big problem because it's short form. We deal in very long form. So this could be negating something 2 paragraphs long. We have not mastered that yet. We're getting better. But there's a lot of good research on it. TF-IDF tends to reward the wrong things. If you're the only person in the room talking about bananas, then the banana idea becomes the discriminator within the logistic regression or whatever you're using there, your SVM. But banana becomes the discriminator. It might not have any real relevance. Latent Dirichlet allocation, really cool. That was the second time I beat IBM, thank you. Assumes that you can describe a topic over a collection of tokens. Like, you have a bunch of basketball team names, maybe this is a topic about basketball, or city names is a topic about cities. That is not true in our domain. One of the things I think is really important when you're doing NLP is to remember that there are domains of knowledge within the human language. You go to college to learn. So to assume that any one NLP package or or routine is going to disambiguate all that is a little bit silly. I think for a very long time, when we get out of the non-trivial examples, I mean, go look at your NLP package. It's going to be sentiment analysis. It's going to be movie reviews. That is not specialized knowledge. We're dealing with specialized knowledge, so we need to be very careful about constructing our features. Next slide, please. So people always say, hey, have you tried deep learning? Yes, I have. I've tried everything out there, everything in the book. Well, not everything. I've tried a lot of stuff. And I'm not saying I did it all well, but I did a lot of it. And I probably could have done some of it better. But the really important things to take away when you decide to do deep learning is that you're probably going to be dealing with an example that has nothing to do with your actual problem. When you pick it up out of the book and it says, hey, we're going to do an autoencoder, it's like, yeah, but that autoencoder is working on a set of data that doesn't have the same correlation structure that you're interested in. You're interested in a very different kind of data. Everybody says to me, hey, what about long short-term memory? It's like, yes, I know about it. I don't need to predict the next token. I don't care about the token level. I care about the concept level. And there's a lot of feature engineering that does go into deep learning that you have to be sort of aware of. Sorry, I'm talking really fast because I'm running out of time, and I still have a lot of coffee. Okay, wisdom of this ancient. I have 2 things I like to say. I like to say, the map is not the terrain. I invented that. No. I invented priming the comp. No, that wasn't me either. When you're storing data and indexing data, you have not analyzed data. So don't tell me that you've done an analysis simply because you now have everything in HDFS, or you can run a MapReduce job against it. When you've done a MapReduce job, you've identified your models, and you've given me a p-value, now you've done an analysis. Or maybe not a p-value, a precision recall curve. Now you've done an analysis. The other thing I like to say, which my VP of marketing wouldn't let me say, is don't ask your bartender if you're an alcoholic. But I had to change it to this. Do stuff that's not within your package. If you're using a particular package and you say, hey, what should I do? And you go, hey, K-means is in my package. I'm going to run K-means. Does that have anything to do with what you're doing? Probably not. Don't let them dictate what you're going to do. Build the math from the ground up, understand what you're trying to get to, and then go find the package. Spend more time reading and less time coding. I think it's important that we try to generate universal truths, right? Especially in our field. We're not messing around. We're trying to deal with something really important, and we're doing our best. And we fail a lot, but we're doing our best. It's the universal truth we're trying to get to. Next slide, please. So these are the things that are in my mind. I'm going to go through this quickly. The very top is, anybody recognize that? Anybody? A couple hands went up. One guy went up tentatively, but I'll bet he's right. That's the Ito calculus. That's an Ito integral from stochastic differential equations. Very interesting to me. I don't know how to use it yet, but it's bugging me that I can't use this on my graphs. It really is. I'm like, this is what I did in graduate school. Lots of things up here. One I want to point out, importantly, is that I've been talking to Cray in Chapel, and one of the things I'm learning about compute is that what's old is new again. We need high-performance computing solutions. We can't rely on some of these JVM-based solutions that have garbage collection who are requiring commodity hardware. Those are important solutions. They don't address my problem of doing things really big and really fast and squeezing every electron out of every CPU. So I'm working with the guys at Cray right now to develop a whole new programming language called Chapel. They've started it. I've become part of their advisory board or something like that in order to make it pertinent to today's HPC environment. I do believe very much that the future is my responsibility. And if I'm going to stand up here and talk about trying to do big things, then I have to get up every day and try to make tomorrow better. And that's a daunting task. Some things make me happy, like ice hockey and robots and Markov chains and sleeping in a wigwam. That was totally fun. Some things don't, like politics right now. And gun control, things like that. These are my social issues I'm sharing with you guys because I have a broad range of things that bug me every day, even from a corporate standpoint. With all that, feeling like the future is on my shoulders, I have to remind myself to stay positive. So please, that's my daughter, of course, with some random pit note. Please stay positive. Please believe in yourselves to change the world in a positive way. I am Brian at deep6.ai, and I'd love to take questions if we have time. Yes, sir. I guess I'm calling you.
So, very good. And the question is, how will you actually change the selection? There's the data process, you guys are doing fast.
Yes. Yes.
Are you actually changing the game, or are you just exploring?
So we believe we're changing the game. I'll give you customer testimonials. I don't know how deeply you know this. I'm going to try to give a quick background. How well you know the field. Maybe you know it really well and you're going to school me, but one of the things that they have a problem when they're trying to identify patients for trials is that, first of all, the software that they're using is not up to the task. And secondly, the data that they're providing is things like ICD-10 codes or CPT codes. And those are like very general codes, like the patient has Crohn's disease. So when they go looking for a Crohn's disease trial, they go get that ICD-10 code. What we're able to do is say, you want to know about their Crohn's disease? We have 15 different attributes that we're able to cross-validate. And we take that directly from the test. So we know how long they've had their Crohn's disease. Is it chronic? Is it maybe induced by their diet? Because the physician has probably made a note. And if they haven't made that note, we're able to surface up the fact that there's missing information here. So on our client sites, they're very impressed by the fact that we go well beyond just like, what code do I need to look up? And then we can retrieve that data in seconds. We had one trial that they were working on for 12 months, and they had 10 patients, and we walked in and got 58 patients in about 10 seconds, validated patients. So we do that because we understand the deep structure of the notes better. I'm happy to talk to you about it more. Yes, any others? Sir, right there in the gray.
How long does it take you to onboard a new class of cancer?
That's an excellent question. You're not from IBM, are you? Because they asked me that. Anybody from IBM? All right. It takes us all of the time it takes to ingest the data. We don't learn the disease. We do it in a very different way. We are very much a data-driven organization, so if you tell me I'm interested in Crohn's disease, you can go investigate Crohn's disease right now and I can bring you patients back. We do that through a variety of semi-supervised learning. We went to the NIH, we learned a lot from NIH, read through a lot of papers, and we have some supervised learning that goes into our product immediately. So I don't need to know anything a priori. 5 minutes ago, if I didn't know anything about Crohn's disease and you asked me about it, I can still give you an answer. So we are disease agnostic. We do, and but they are not specific to a disease. But what we do is we look at the correlation structure over the entire graph, and we unpack a lot of that information from the data itself. And we're told we're pretty accurate. I mean, it's hard to give you a precision recall number or something like that because there's thousands of diseases out there. But we do have some sort of sneaky ways we get around that problem of having to learn everything in advance. We don't know anything in advance. We can deal with it right now today. Do we have time for anything? All right, thank you very much, guys.
Hey, so good news. I get to it. So you're my guest. When you go to the registration, just ask for Arnold, and your guest in profile percent under one of those. Okay. I think those fairly. I actually checked it. It's actually on. There's an afterwards. But yeah, I mean, and also there's probably
There's a lot to jump on. He's probably like the best speaker. This whole bar.
I was like, oh, okay, thank you. Yeah,
It's an integral problem. Forget what the heck this is, China.
and they have
Showcase for the next one? I'm not sure. Not sure? Check.
Go check the app. Technical links.